The analysis step in SoundCheck has a lot of different settings in it. There's a lot of different things we can do, different algorithms, different tabs for configuration. We're going to talk about a couple different parts. We'll look at Harmonictrak, specifically the Distortion tab, measurement confidence, how to configure loose particles, and then using realistic test signals. For a lot of these different sections, we're only going to kind of cover how to set them up, some basic use cases, but we also have a lot of resources available on our website, AES papers, videos, and other brochures, etc., that go into a lot more detail on how to use these algorithms, the theory behind them, and some more deep dives. Those are linked in the presentation, and if you ever need to investigate a topic further, something that catches your interest, please dig in. We have a lot of information available. So what is the analysis step? What's its role in SoundCheck? If we think about a basic electroacoustic test, how we usually run it is we define a stimulus that we're going to play. We apply that stimulus to our device under test through an acquisition. Then we compare the stimulus waveform with the recorded time waveform that came from the acquisition step. With a combination of those two, we'll run those through the analysis step to compare, and that analysis step is going to output a lot of different data. So we're usually going to be analyzing time waveforms. Again, most often it's a stimulus and a recorded time waveform. But some analysis can be done outside of this workflow. For example, an RTA or FFT doesn't need a stimulus, and we could do analysis with just a recorded time waveform. Alternatively, if we were doing open loop testing, where we were recording on a different device, we could recall wave files into SoundCheck without actually having an acquisition step and analyze it the same way. We also would have the option to group different waveforms together and analyze them in one step. If I had an 8-channel mic array, I could group all of those microphones together, send those into the response section of the analysis step, and my analysis editor would give me 8 different curves for those 8 different waveforms. When we select an analysis step, the first thing we want to do is pick which algorithm to use. This will depend on the signal type, if I want to use step science sweep, if I want to use noise, if I want to use a log sweep, and the desired output. As we change the algorithm we're using, the outputs will be different. So some common things that analysis step would output could be frequency response, distortion, impedance, impulse response, a time envelope, etc. When we open the editor, it looks something like this. In the top left is where we're choosing the algorithm to start working on. Once we pick the algorithm, there's 8 different tabs we can configure. Some of them are going to be the same across all algorithms. Waveforms, for example, always looks exactly the same. We pick what type of measurement we want to do, absolute or relative. We pick the stimulus waveform. We pick the response waveform. But something like distortion is going to change completely depending on the algorithm we're using. These are all very dependent, so make sure that if you configure one for one use, as we're switching algorithms and anything change, make sure it's still appropriate for the different measurements. What we're going to concentrate on today a little bit more in depth is first looking at the Harmonictrak algorithm and the Distortion tab. So with Harmonictrak, we need to use a stepped sine sweep stimulus. There's a couple different options here. We can use a frequency step sweep, which is a step sine sweep. We'll also call it a sweep in SoundCheck stimulus terms, or a two-tone stimulus. A two-tone stimulus can either be intermodulation or difference frequency. This algorithm will measure the frequency response with tracking filters. So as we're sweeping, as we're stepping throughout, we're going to filter out everything except for the exact frequencies we're stepping in the stimulus. That'll be able to give us our frequency response. And in addition to the frequency response, we're also going to be measuring individual harmonics. These individual harmonics can then be used for distortion measurements. We can get things like THD, THD+N, rub and buzz, and perceptual rub and buzz. Harmonictrak and TSR are two algorithms that on this distortion tab will be able to get us a lot of this data. So we have a step sine sweep, we open up Harmonictrak, and when we get to the distortion tab, the first thing we'll need to do is pick the distortion type. This is completely dependent on the stimulus in use, but it changes this distortion section to reflect the type of distortion selected. So what we're looking at here is harmonic distortion. I get a list of harmonics available. As I enable these harmonics are going to be output to the memory list. Here I have harmonics 1, 2, and 3 selected. That means I'll get the frequency response, harmonic 2, and harmonic 3. This also will affect which harmonics are used to calculate the different distortion parameters. If I have THD percentage enabled, I'm also going to output THD to the memory list. So I'll get a total harmonic distortion, and that's going to use the 3 harmonics I have selected in that dropdown. So if I run this step, I'll get an output of harmonics 1, 2, and 3, so the fundamental harmonics 2 and 3, as well as total harmonic distortion using harmonics 1, 2, and 3 in the calculation. If instead of a step sine sweep, I was using a two-tone intermodulation stimulus, I could switch this harmonic type distortion to intermodulation. When I switch this over, the harmonic distortion section we were just looking at in the middle switches to intermodulation distortion. Here, I can specify which orders to include in my calculations and to output to the memory list. Then the same thing will happen with difference frequency. If I enable the difference frequency radio button, I will output different orders expecting a difference frequency stimulus input. I can specify the orders and then the type of distortion I want output. So now let's talk about just distortion, what we're trying to catch, what the different use cases of a step sine sweep versus two-tone would be, what's going to be found, what can we use to get data for us. So if we think about distortion, it's we put a frequency into our device under test, and then extra frequencies get output. if I put in 100 hertz, if my device was perfectly linear, on the output, I would get 100 hertz. But most devices will give us other frequencies on the output. This can be harmonics, possibly intermodulation frequencies, noise, a lot of different things. So we can try and measure on the output what's coming out and try and have that tell us things about our device under test. For example, if we put in a pure tone sine wave and we get asymmetrical nonlinearity on the output, which is compression on the positive going waveforms, when we look at the spectrum, we'll have even order distortion products. So again, I put in 100 hertz. Some of that energy is going to be transferred for the fundamental to the second harmonic, the fourth harmonic, sixth harmonic, etc. In this type of distortion, there's going to be a relationship between the excitation frequency and then the distortion products. And again, in this case, they're going to be multiples of each other. And for this type of distortion, it's the even order multiples. We could also get symmetrical nonlinearity. Instead of just compression in the positive portion of the waveform, we could get compression on the positive and negative side. This will look almost like a square wave, and the ear doesn't really like square waves. For the output, we'll be giving 100 hertz, for example, and we'll be getting odd order distortion products back. So 300 hertz, 500 hertz, 700 hertz, etc. In the real world, we're never going to just have even or odd number harmonics. We're going to have a mixture of both. But how much energy lives in different parts of them, if there's more energy in the second and the fourth than the third and the fifth, that could tell you something about your device. It could be some manufacturing defect that you need to catch. It could be something about the design. But it's going to tell us information about our device because of what harmonics are coming out when we input a single frequency. Instead of just putting in one signal at a time, we could use a two-tone stimulus. For this, we're putting two tones into a nonlinear system, and on the output, we're not just getting those two tones, and we're not just getting harmonics of those. We're getting completely new frequencies. These are going to be different linear combinations of the two original frequencies and are called orders. Before, when we were looking at intermodulation and difference frequency distortion types, we could select orders from the drop-down list. This is what we're talking about. They don't have a harmonic relation with the original frequency, unlike harmonic distortion. The first type of two-tone stimulus is intermodulation. This is built of a frequency step sweep plus a fixed tone. So one signal will always play one frequency, then another signal simultaneously will sweep. Difference is two simultaneously frequency step sweeps with a fixed hertz difference or ratio difference. For example, I could sweep from 10K to 100 hertz and then simultaneously sweep 100 hertz less than that at the same time, or a third octave less than that at the same time. But the difference between F1 and F2 will always be the same. It's just either going to be fixed hertz or fixed ratio difference. So why would we use these? What benefits do they have over pure harmonic distortion. For intermodulation, it's really helpful because it can help detect amplitude and Doppler modulation. This is caused by a low frequency signal that's producing large excursions. So that fixed tone in the low frequency, in combination with a higher sweeping tone riding on that low tone, can give us amplitude and Doppler modulation that we might not catch if we're just putting out one tone at a time. Another really interesting use case of this is to calculate microphone distortion. If you try and use harmonic distortion to find out how much distortion is on a microphone, you need to be playing your signal out of something. And that something, that source speaker, will often have more distortion than the microphone you're trying to test. So no matter how much you're calculating harmonic distortion, no matter what microphone you're using, you're really just measuring the distortion of the speaker. Now, it depends on the quality of both the speaker and the microphone, but as a general rule, that's the case. What you could do instead is define an IM signal, and then instead of playing that out of one speaker, you could play the fixed tone out of a subwoofer, then play the sweep out of a full range speaker. When you calculate harmonic distortion on the microphone, that might be caused by the speakers, but every part of the intermodulation distortion is caused by the microphone because the speakers aren't individually playing the two tones, so they can't be causing the IM distortion. We have an example sequence of this available on our website, and I recommend downloading that, trying to run it, and it is a very interesting and good use case to try and use the IM distortion. Difference frequency is very good at detecting distortion at frequencies where the single tone distortion would fall out of the frequency range. You can think of this as if I had a band-limited device where I can't play a frequency above 8K, trying to get harmonic distortion at 5K is a problem because the second harmonic there at 10K is already out of my passband, so I'm never playing the signal. But using difference frequency, I could find those distortion products in the passband of the device. So now, how do we pick which frequency and level to use for the two different types of two-tone? For intermodulation distortion, F2 will be the fixed frequency, and F1 will be the swept frequency. F2 is usually 12 dB greater than F1. And for the frequency itself, the minimum that F1 should sweep down to should be greater than F2 plus 14 divided by the minimum duration. So what does this mean? If we're defining our sweep in the stimulus editor, we can define how many cycles or how much duration to spend at each step. If my minimum duration was 100 milliseconds, so 0.1 seconds, then I could use 14 divided by 0.1 equals 140, and let's say F2 was fixed at 40 hertz. That would be 40 hertz plus 140. F1 should not sweep below 180 hertz. This is just to make sure that we have enough signal, that the difference between the two is large enough to get the data we want. If we get too close, or we don't spend enough time at each step, we might not be getting as much data as we need to calculate the IM distortion. As we're sweeping F1, the interval between the products equals F2, so whatever frequency we defined there. And as F1 sweeps, the products are going to follow along as a group. The nth order is caused by x to the n characteristics. And for the orders, positive is above F1 and negative is below F1. For difference frequency, F2 and F1 are usually equal in level. The difference between the two should be greater than 14 divided by the minimum duration. So the difference between the frequencies, either linearly or a ratio, is held constant during the entire sweep. The interval between the distortion products is the difference between F1 and F2. The odd order products follow as a group with F1 and F2 as they sweep. But the even order products are fixed in frequency. So down the -2, -4, and -6 labeled over here, these will stay the same no matter what F1 and F2 are doing as they sweep. And the nth order is caused by x to the nth characteristics. Positive is above F1 and F2, negative is below F1 and F2. So let's think of the example of a band-limited device. Here is a device that can't play above a certain frequency and then falls off below another frequency. If I'm trying to measure, say, 4.5K and trying to get distortion products there, well, the second harmonic is already out of the passband. And when you think about it, really the second harmonic distortion can only be measured in the lowest half of the passband, and third harmonic distortion can only be measured in the lowest third. And as you try and get to higher orders, we're narrowed down to even smaller frequency ranges. So IM products for intermodulation will fall within the passband. The problem here is the low frequency. If the device itself has a low pass and anything above 8K is a problem, but you can still play low frequencies, you could use IM distortion. But if you can't actually play that signal in the low end to get the intermodulation, then we can't get intermodulation distortion. But difference frequency distortion. As we're sweeping with F1 and F2, the odd order products fall within the passband. Remember, the odd order products are following with F1 and F2 as they're sweeping. We can use this over a really wide frequency range if the difference between F1 and F2 is small. But the even order products might fall below the passband. Those are fixed. There's no way you can change where those are without changing the difference between F1 and F2. So if your device doesn't play out in the low end, you might run into an issue there. But the odd order difference frequency products can really help testing in very narrow band limited devices. As you're trying to test your device using this data to correlate to some sort of physical mechanism, here's just a quick cheat sheet of common use cases. This isn't an exhaustive list nor a complete list by any stretch of the imagination, but it's a good starting point where if you saw your third harmonic had a lot of energy in it, you could look into the displacement limit. If there's misalignment, that might cause a high second harmonic. And cone breakup might be shown in the third difference frequency. microphones with second and third order intermodulation, and rub and buzz may be caused by a bent frame. This would show itself in the high order harmonics. When we look in the Harmonictrak Distortion tab, no matter what we have selected, harmonic, intermodulation, or difference frequency, there's an option at the bottom for what method to use, IEC or IEEE. This will change how the distortion is calculated. Both of them will output the same types of data. The math on them is just a little bit different. So you want to make sure if you're setting up a bunch of tests that you understand the difference between the two and you have the one selected that you want to be using. For THD IEEE, the percentage of THD equals the square root of every harmonic we have selected squared added together, divided by the square root of the fundamental squared times 100. That's what's going to give us our THD percentage. It's relative to the measured level of H1, which is the fundamental, only. The other option is IEC. This will have all the harmonics we have selected in the numerator. So if we have selected H1, H2, and H3, H2 and H3 will be in the numerator, but the big difference between the two is in the denominator. Instead of just the fundamental, we have H1 plus every other harmonic we have selected. So the distortion is relative to the measured level of H1 plus the harmonics. IEC or IEEE will also affect how intermodulation and difference frequency is calculated. For IEEE, we're going to have 100 times the total intermodulation divided by F1 squared plus F2 squared, take the square root of that, where F1 is the intermodulation fundamental and F2 is the fixed tone. And for difference frequency, F1 is the upper fundamental and F2 is the lower fundamental. For the IEC definition, the numerator is the same, but the denominator is just F1 plus F2. As we're selecting harmonic distortion, instead of just rub and buzz, we have, instead of just total harmonic distortion, we have an option to select rub and buzz or perceptual rub and buzz. These are going to be calculations for higher order harmonic distortion, and we'll look at why those might be helpful to look at instead of just pure THD. So all distortion isn't created equally, and this has to do with a threshold of hearing and how the human ear will interpret different sounds and the harmonics as they get closer or farther away to the fundamental. If a pure tone is slightly above the threshold of hearing, then the lower order harmonics can be easily heard. So if at 1K we were outputting 20 dB SPL, we could hear harmonics 2, 3, and 4 pretty easily. But as we increase the tone's level, then the masking curve is going to broaden at higher frequencies. So the second harmonic here could be as high as 10%, but still be inaudible. So H2 of 1K is 2K. And that could be only 20 dB down, but the human ear wouldn't be able to hear it because it's getting masked. On the other hand, if the 10th harmonic is at 0.1% distortion, the human ear would be able to hear that. So even though H2 and H3 might have much higher actual levels, that way your total harmonic distortion will be a higher percentage, the human ear might not hear that as a negative thing. It might be completely masked by the fundamental. Whereas higher level distortion around harmonic 10 will be much more audible and sound much worse to an end user. So the calculation for rub and buzz is the same exact as total harmonic distortion. Within the numerator, it has the harmonics you have selected, but the only difference is rub and buzz will only calculate harmonics that are greater than the 10th. If in my editor I selected harmonics 1 through 20, then I'm only going to put harmonics 10 through 20 into my rub and buzz calculation, but THD will take in all of them 1 through 20. So here is a use case where rub and buzz was able to tell us a little bit more information about a device than just THD. These are spectrums of two identical model car speakers. The top one was subjectively judged to be good. When people listened to it, they said, yes, I would sell this. I'm happy with how it sounds. It's great, ship it. The bottom one was subjectively judged to be bad. This is the spectrum with 200 Hertz, and the top one has 6% THD. But if you look in the higher order harmonics, there's only 0.02% rub and buzz. There's not a lot of energy in the high order harmonics. So a normally functioning loudspeaker will have a high THD, but low rub and buzz. If we look at the graph of the bad speaker, there's only 2% THD, but a lot of that is concentrated in the high order harmonics. So the rub and buzz here, instead of 0.02%, is 3%. That is much more audible, and it's not getting masked by the pure tone at 200 Hertz, and it's not as pleasant to listen to. So this was being caused by a rubbing voice coil from a bent frame. So even though the THD was much lower than the good speaker, rub and buzz for this specific use case was able to capture what sounded good and sounded bad. And really that's the goal of these measurements. We want to make sure that the limits we set on harmonic distortion or the limits we set on rub and buzz actually correlate to something that sounds good or sounds bad. And in that vein, instead of just rub and buzz, we offer the option to output perceptual rub and buzz. This will correlate to human hearing to show audible distortion. It uses masking curves that correlate to filters inside the human ear to help determine audibility. So instead of just globally saying everything above the 10th harmonic is audible, or every harmonic is equal when we're calculating the level, we're actually taking specific masking curves and some more things behind the scene to correlate to what a listener would be able to hear. The loudness of rub and buzz is in phons rather than a percentage or dB. So we're not just comparing it to the fundamental level, we're trying to say, will something be audible? There's also a threshold on this. So if we don't have any audible rub and buzz, PRB will output 0 phons. So here is what we actually run through everything to get rub and buzz on an output. So there's a harmonic structure, there's different algorithms to correlate for what the human ear will actually be able to hear, what internal noise in the body is going to mask things, different frequency, partial loudness, etc. If you want any more information on this, to go through all of these steps, we have a paper on the website, which I'll link in the end of this section, and it's available on the slides that were sent out, that goes really into depth of how this is used and kind of the theories behind it. Another option to output is the total distortion. The total distortion is going to be a power sum of all of the harmonics we have selected. Unlike THD, percentage, or rub and buzz, we're not comparing the harmonics to the fundamental. We're just getting the power sum of the harmonics selected. This is going to be output as whatever unit your harmonics are in. So if you're measuring a loudspeaker and your units are in dB/SPL, then total distortion will output a total distortion curve in dB/SPL. The bottom section underneath the Harmonictrak, the bottom section underneath the harmonics list is distortion and noise. For this, we can enable THD+N. There's options to specify and enable a high-pass filter and a low-pass filter, as well as a synthetic notch filter. So what this synthetic notch filter does, and let's think of this in contrast to how traditional THD+N used to be measured. So we put in an excitation frequency, we get harmonics, and what we want to measure is everything except the orange frequency that we input. So we traditionally and conventionally, this was filtered using a tracking notch filter. All of the noise outside of this filter, the harmonics, are going to be added together and give us our THD+N. The drawback here is that this filter removes all of the noise that's inside the filter. So anything close by to that excitation frequency, we're removing from our measurement. So THD+N is going to be underestimated. With that synthetic notch filter enabled, we're going to remove that excitation frequency with a very narrow digital notch filter. When we calculate the noise, we're going to include that little bit that used to be taken out from the old style filters. So THD+N with a synthetic notch filter is very accurate. But if you're trying to compare measurements from SoundCheck to maybe measurements you took years and years ago, measurements on a different system, we can disable that synthetic notch filter, which will give us a lower THD+N percentage. It will be less accurate, but it's going to be more comparable to the older style of THD+N. In general, THD+N is a good measurement for electronic devices. But if you're trying to measure transducers, like a loudspeaker, then the background noise is going to be so much higher than the distortion, measuring THD+N isn't really an appropriate measurement. For something like that, you'd care more about THD or rub and buzz, perceptual rub and buzz, etc. The noise from the background, the noise from just the room you're in, is going to skew the measurement so much, it's not really something that's going to be very helpful to get data back from. So if you're doing any sort of transducer testing, I would stick with THD. If you're trying to measure how much noise an electronic component is introducing to your system, then THD+N is a great way to do that. Harmonics at measured frequency, as well as THD and rub and buzz normalized, are very related. So when we select the harmonics from the memory list, we're outputting those harmonics. Harmonics at measured frequency will also output those harmonics at the measured frequency. THD normalized and rub and buzz normalized is the distortion calculated as if the harmonics were plotted at the measured frequency. So what does that mean? Why is that helpful? Why would we ever do that? If we think of this in context of an actual use case to measure THD, we can think about we're putting in the signal into a nonlinear device. If our device was perfectly linear, we wouldn't need to test it, it would be perfect. But most things will have some sort of amplitude irregularities. In the passband, it might be accented in some areas, it might be attenuated in some areas. And especially in the high and low frequencies, it might completely roll off. So if I sweep from 20 hertz, then my second harmonic will start at 40 hertz. My third harmonic will start at 60 hertz. The difference between all of these is going to be the same. Let's assume that I have a device where every harmonic is 20 dB lower than the one before it. When you plot these harmonic curves the traditional way, you take the second harmonic and you place it starting at 20 hertz. You take the third harmonic, you plot it starting at 30 hertz. This was done for a couple of reasons. So, in the past, analog test equipment was synchronized to the signal generator. So as you were playing 20 hertz, you were drawing your fundamental, you were drawing your second harmonic, you were drawing your third harmonic, etc. And it's also a little easier to read distortion in a percent by comparing the harmonic to the excitation frequency. So all THD that's on published materials, most spec sheets are going to have distortion using this method. The problem is the interpretation of the results. If we're thinking about the low frequencies, instead of plotting at 40 hertz, we're plotting at 20. So we might be overestimating this low frequency distortion. And in the high end, we may be underestimating the frequencies because of these roll-offs. In the passband, it's going to depend on the exact frequency we're talking about and the exact response of the device under test, but you could be over or underestimating the distortion, depending on where some of the peaks and valleys are in the frequency response and amplitude linearity. So instead of traditionally measuring the THD like this, by measuring the THD at the measured frequencies, it's going to remove the effect of the DUT frequency response, as well as the frequency response of the test space and any irregularities there. And it's going to actually plot the harmonics where they occur and give us a more accurate representation of where the distortion is being caused. So again, traditional distortion, the fundamental starts at 20, second and third also both start at 20. But if we think about normalized distortion, that would be we start a sweep at 20, the second harmonic starts at 40, the third at 60, etc. So I'm going to open up SoundCheck and we'll take a look at some of the different options that are in there and how this distortion will actually compare traditional versus normalized. On this screen, in the top left, I have my fundamental in blue, then harmonics 2, 3, 4, and 5 drawn underneath it. You can see they all start at about 100 hertz. And in the top right, I have my fundamental with high order harmonic distortion starting at the 10th, so 10 through 15. Underneath, I have total harmonic distortion, the traditional way, calculated with the harmonics. And over here, I have traditional rub and buzz calculated with these harmonics. In the very bottom, I have perceptual rub and buzz. So with this algorithm and this device under test, because no actual audible rub and buzz was detected, my perceptual rub and buzz is a flat line at 0 fons. Now let's compare this to the harmonics at the measured frequency. So here I still have my fundamental with the same number of harmonics, but instead of plotted traditionally, they're plotted at the measured frequency. In green, I have my normalized THD, and in red, I have the traditional THD. You can see, especially in the low end, how accented the traditional is and how much flatter the normalized is. In the passband, though, we can see around 1K, traditional is higher, around 5 or 6K, normalized is higher. So it's dependent on the exact frequency response of the device, but we're going to see a little bit of change in there. The same thing happens with rub and buzz normalized and traditional rub and buzz. Normalized looks a little bit flatter in the low ends, then we get a little bit of a difference, especially in the higher ends, with the amplitudes that are higher. This can make it a little bit easier to set limits. So if I was trying to set limits on THD, I would often try and have something that goes up really high in the low end because I know my distortion goes that high. But it might be a little bit cleaner to use normalized THD. I could set limits that are a little bit flatter that will not be affected by the frequency response of my DUT. It might be a little bit easier to manage and visually see where some of the issues might be occurring. We can also look, that was a speaker with a pretty good response with not a lot of distortion. We could also see some of the differences if there's a lot of distortion. If we can see in the low end, we're getting up to 30% THD, we're getting up to a really high amount of rub and buzz. And then if we look at the perceptual rub and buzz, instead of being a flat line at 0 fons, we're going up to 70 fons across here. There's some amount of distortion audibly. There might be a problem with this device, whereas the first device looked a lot flatter with a better frequency response. And if we look at normalized, we'll see similar things. So in the low end, we're still seeing a lot more accented for the traditional methods of THD and rub and buzz, but normalized, we still have a much higher percentage than the good device. If we look at the analysis step itself, we can see some of the settings that we've been talking about. So if I open this up, I'm on the Harmonictrak algorithm, and I can look at the Distortion tab. So in here, I've manually selected the harmonics I want to use. So I have 2, 3, 4, and 5. Those are getting output to the memory list. I'm also using a group to look at harmonics 10 through 15. Instead of having to manually click on a bunch of different curves, if you have an exact range of harmonics you want to add, you can click this Edit List button and say I wanted to look at harmonics 7 to 14. I could add this into my memory list, and to just quickly enable all of those curves, I could just click this one button. Those harmonics are going to be calculated, added into my distortion, and then output to the memory list. Another useful option, because we can go in here and manually select or deselect curves, is see distortion caused by single harmonics. If I knew that I'm really interested to see what is caused by my third harmonic, I could just look at the THD, select 1 and 3. Then when I run this step, my total harmonic distortion only really has one harmonic selected, so I can see the distortion caused by that. As I added more, I could see how all of my distortion would change, how that would be updated to reflect that. So I mentioned this a little bit before, but some papers we have are available on our website. If you go to listeninc.com, under the resources, we have a paper for the THD+N algorithm that goes into a lot of calculations on that, use cases, how we came up with it. There's a paper on practical measurement of loudspeaker distortion, which relates to perceptual rub and buzz, and audio distortion measurements, which just covers a lot of different distortion topics. So if you want more applications of these, a little bit under the hood of how the math is done, but definitely recommend to go and read into those a little bit more. So now we'll look at measurement confidence. Measurement confidence is going to help us see how close we are to our actual measurement instead of measuring noise, right? So in the Harmonictrak distortion tab, we have this group of options called measurement confidence. So again, it's really how confident the algorithm is in the data it outputs, both the fundamental and the harmonics or the orders. It looks into the signal and it looks into how much noise there is and says how confident is the measurement that I gave. So really, any measurement has a level of uncertainty. Part of this is going to be due to noise. Noise adds randomness to the level. If we're in a really noisy environment and we're trying to run a step sine sweep and we're not spending enough time at each step, and something happens to change the level of the noise in the room, and I run the test again, I might be getting different results. The total noise of the measurement is known. As we're running this algorithm, we know the total noise. This can be output to the memory list in the measurement confidence checkbox. So the RMS level of total noise for each stimulus frequency, or if we're using IM or DF, frequency pair. Since we know the noise, we can then calculate the standard error of the estimated level. So with a measurement of x and a standard error of sigma, the confidence that the true value of x is between the limits of plus or minus sigma. If we have x minus 1 plus 1, we have 68% confidence. Plus or minus 2 is 97% confidence. Plus or minus 3 would be 99.7% confidence. These are the confidence limits. The standard error, based on one standard deviation for the fundamental and every harmonical order selected as output when standard error is enabled. So similar to outputting the fundamental plus the harmonics we have selected, it's going to give you the standard error for all of those as well, for whatever we have selected, either the harmonics or orders depending on the type of distortion we're calculating. The confidence limits get output as two curves. There's the measure curved plus or minus a sigma, where the factor A is chosen by the user. Inside the analysis editor, when I'm enabling my measurement confidence, I could specify A to be 3 if I want to be within 99.7% confidence. So here is a suite where I had a pretty short duration defined in the stimulus, and there was a lot of noise in my measurement. What I did was I enabled measurement confidence, and when I output my fundamental, I also output an upper confidence limit and a lower confidence limit. So looking at this, it's telling me that my measurement really isn't very accurate. If I ran this measurement again, I have maybe a 10 or so dB swing throughout different frequency ranges that maybe were caused by noise, maybe SoundCheck didn't get enough signal, the microphone was too far away. Especially if we look over in the high end, we can see around 7K or 8K or so. The lower confidence limits really falls off a cliff. It goes down to about negative infinity. And that's telling us that SoundCheck really measured either a lot of noise and not enough signal, and something isn't completely accurate with this measurement. So I enable these. How do I make this better? Every time you run an acquisition step, the acquisition outputs a max FSD. If the acquisition max FSD is below minus 30 dB, which is basically 0 dB is the full amount of signal available on that input, we want to try and increase that. So we want to get between 0 and minus 30. We could try to increase the input gain. If I have a microphone power supply with 20 dB of gain I'm not using, I should enable that gain. If I'm using any listen device, I could enable auto gain. That will automatically try and get the best gain range possible to get as close to 0 without going over. And that's going to automatically set the gain on my device to help me do this. I could increase the stimulus level or decrease the test distance. If I'm outputting 50 dB SPL from 10 meters away, no matter what I do, my measurement's going to be very noisy because that signal isn't traveling very far. It's going to not have enough signal to noise ratio, and it's going to be not confident in the actual measurement. So you could try and increase the stimulus to a point where you're within that range again. You could bring the devices closer together if they're very far apart. In the stimulus step, we could also increase the minimum cycles or minimum duration. Remember a step sign sweep, steps between frequencies. It spends a certain amount of time at each of those steps. If I'm only spending one cycle at every frequency, I'm not going to be able to reject all the noise around it. I'm not going to be able to calculate what's actually signal, what's noise, what's randomness. The longer we spend here, the more noise we're able to reject. This becomes a pretty large give and take, especially during production. If you're doing production tests, you're often in a noisier environment and time matters a lot more. So it becomes a little tricky to decide how long should my stimulus be before I'm having negative impact of that. I want to be as short as possible, but I want to make sure that the data I'm getting isn't too noisy, is actually accurate. And one way to really help this is using this measurement confidence. You could enable these, change your minimum cycles and minimum duration around, create compound stimuli with different minimum cycles and minimum durations in different areas until you've reached a balance of speed versus accuracy. It could also help to try sweeping from high to low. If you sweep low to high, you'll be introducing a lot of signal and energy at once into the device. Sweeping from high to low will sometimes help that, make it a little bit more accurate. And increase the bit depth. If instead of 16 bits you could record at 24, you might be helping yourself out a little bit there. So on my device, I did some of those things, and I reran my test. I can see I'm getting much closer now. These upper and lower confidence limits, instead of about a 10 dB window, are almost right on top of each other. One thing to note here is the low end, though. Even though most of my signal is pretty close, and something you can often see is where my device isn't outputting a lot of signal because I might be rolling off. No matter how long I sweep there, no matter how close I am to my device, I'm not going to get a lot of confidence there just because my device isn't outputting a lot of signal. If instead of stopping at 100 Hertz, I swept down to 20, this would look even worse. My confidence would be pretty bad just because my device doesn't play that low. So if that's something that you end up seeing, then know that the measurement you're getting is most likely not as accurate because your device isn't putting out enough signal. This is going to really help illustrate some of the points. I'm going to open it up on my end, and this will have to do with the cycles in minimum duration, how to best optimize these, and to see what effect this will have on your confidence. This sequence also comes with a PDF. This will go over how to set up your device, a little bit more information on it, and tell you how to set this up. So if you want to run this at home, walk through the setup diagram. On my end, I'm using an Audio Connect with the SCAMP and an SCM measurement microphone with the device under test speaker, but any audio interface or microphone would work here. What we're going to do is run 3 different sweeps with 3 different minimum duration and minimum cycle times. We'll see what the frequency response looks like, what the average standard error looks like, as well as what the confidence levels look like at different frequencies. Okay, so the first sweep outputs this curve here. The frequency response is in blue. The standard error is here in orange. And the positive and negative confidence limits are in red. So this range, even in the passband of the device, is pretty wide. I have almost a 15 to 20 dB window here. SoundCheck is really not positive of how much of this is signal, how much is noise. And at the high end, you can even see the signal gets completely cut off. We're losing signal somewhere. Something went wrong in our measurement. The confidence limits here go down to about -infinity. They just completely fall off a cliff. The same thing happens in the low end. If we look at how this stimulus step is configured, oops, no, this one. So I'm running a frequency step sweep. The start, stop, and resolution and level are going to be the same across all of these. The only difference is the step size. So here, I'm spending 3 cycles at every step from 20K to 20 Hertz. In the low end, this might be enough. In the high end, it's really going to struggle to get any sort of data there with only 3 cycles at 20K. The next curve for the second sweep is showing us a lot closer together in the upper and lower confidence limits and a much lower standard error. In the high end, though, we're still a little bit off. We still have some sort of discrepancy. So we're looking a lot better in the passband, but in the high and the low end, we're really not that accurate still. This stimulus is configured for 10 minimum cycles. The duration is increasing from 740-ish milliseconds to 2.4 milliseconds. So this second sweep takes almost 2 seconds longer. But you can see by going from 700 milliseconds with 3 cycles to 2.4 seconds with 10 cycles, how much more accurate the measurement is. We're not seeing that behavior where the high end is completely cut off. We're getting data everywhere. And the last sweep is going from 20 to 20K. And now in the high end, we're almost completely on top of the upper and lower confidence limits. So we're extremely confident down to about, say, 100 Hertz. And this is what I was talking about before. I could put as much signal as I wanted. I could spend as much time as I wanted. But the device I'm using is not putting out a lot of signal at 20 Hertz. There's going to be a lot of noise. It's not going to be that accurate. But this does tell me something about the device. As I increase this, how much more accurate am I going to get? The answer is probably not a lot in the low end. But why are we so much more confident in the high end? If we look at this stimulus, we still have 10 cycles enabled, but instead of 0 minimum duration, we now have 10 milliseconds. The length of the sweep went up from 2.4 to 2.5. So not a much longer sweep time. But why does that benefit us so much? At every step, SoundCheck is going to satisfy both the minimum cycles and the minimum duration. So at 20 Hertz, it's going to satisfy whichever is greater here, which is 10 cycles. The change comes above 1K, because above 1K, 10 milliseconds is longer than 10 cycles. In the high end, we start spending 10 milliseconds at each of our steps. This really helps when we get to about here, around 13K, how much more confident we are in the measurements because of only having a few cycles, which in the high end is not a lot of time. Being able to define time and cycles without spending a much longer stimulus length, we're getting a much more accurate and confident measurement. You can see especially here in this standard error, where it's a pretty close in the passband, but as we get higher and higher above 1K, it's going up much more here, but in this third stimulus is going down a lot more. So that's one way we can use the stimulus editor to try and get as much confidence in our measurement as possible without sacrificing too much time. And again, if I'm on a production line, I could really start playing around with this, start deciding how accurate do I actually need to be, how much noise am I okay with, to make sure that I can run these tests as quickly as possible. Loose particles was an algorithm designed to detect loose particles of foreign material trapped inside of a loudspeaker. When these particles will hit the diaphragm, they'll cause a pop or click noise. These impulses aren't really frequency-based. They're going to occur at random times, so trying to use frequency analysis won't always catch them. If I just wanted to use THD, it might not always find these type of transients. The application used, though, is much wider than loose particles. So the name itself kind of connotates what you should use it for, but it can really find any type of transient distortion. This has been used before to catch digital dropouts and glitches, for air leak detection. Anything that's going to be non-harmonically related and cause transients in your waveform will be caught with loose particles. Loose particles is available with every algorithm type. So if we're using Harmonictrak, heterodyne, TSR, RTA, doesn't matter what we're doing, we can enable loose particles and set that to catch any loose particles in our device. So here is a waveform, and this is what we're catching. We're catching randomly spaced occurrences of transients. The spectrum is random noise. There doesn't have to be a distinctive pattern. And these are usually randomly spaced, and they're so far apart they can be heard as distinct events. So it can be similar to rub and buzz. It can catch some things in there as well, but a lot of times it will sound, instead of like a continuous, it'll sound more randomized and as distinct events. Here is the editor for loose particles. It has its own tab, and all you need to do to get going is enable the loose particles checkbox. After enabling the loose particles checkbox, we could also output the loose particle waveform. This is very interesting because what it will do is take the recorded time waveform, strip out the stimulus from it, and allow you to listen to everything else. So this will show you what the loose particles sound like, but it could also show you what the rub and buzz sound like, what the distortion sounds like, because all of those are not the stimulus. So even if you're not interested in catching loose particles, by outputting the loose particle waveform, you're outputting a waveform with the stimulus stripped out. And as you're trying to design tests, as you're trying to listen to devices, listening to the loose particle waveform can be a really quick and easy way to hear any of the defects that might be masked by the stimulus itself. Loose particles outputs an integer. It tells you how many counts of loose particles there are. So what we're doing in the threshold area is defining where are the limits and above which point will a loose particle count. Absolute versus relative will change to be either absolute or relative, and that's going to affect the attack threshold. Relative will normalize the loose particle envelope to 0 dB. So if I have 8 dB relative, that means every time my envelope goes up 8 dB from the normalized level, I have a loose particle count. If I'm using absolute, that's going to depend a little bit more on the device under test at the levels I'm testing. That might require a little bit more experimenting, looking at your specific envelope to see which levels are appropriate for setting your own limits. Averaging is the averaging time to get the spectrum, and max stimulus frequency is a high pass. It's going to strip out any data below the frequency listed. For minimum and maximum duration, these are the points where we're actually going to count a loose particle that exceeds the threshold. Let's say that my minimum duration is 5 milliseconds and my maximum duration is 15 milliseconds. In this first example on the left, I have a transient in the envelope that's 3 milliseconds long, go above my threshold. My minimum is 5 milliseconds, so I don't count this as a loose particle. The other, in the middle, is 8 milliseconds long. That exceeds my threshold, and it gets counted as a loose particle. And all the way to the right, this was above the threshold for 17 milliseconds, but 15 milliseconds was my maximum. So this does not get counted. With this case, I would only have one loose particle count. The threshold also interacts with the hysteresis. we can set this usually as a negative dB number. What this means is when my envelope crosses the threshold, it has to go down n dB until it can go above the threshold and count again. If we look at this envelope on the left side, I exceed the threshold, but don't go 6 dB down below the threshold until the second red arrow. So with a negative 6 dB hysteresis, I get 2 counts on my loose particle algorithm. If mine was set to 0 instead, then you can see all that it would care about would be every point that exceeds the threshold. So that would be the 2 red counts plus the 4 green counts for a total of 6. This is to make sure that if you have something that's hovering right around the threshold and just oscillates back and forth a lot of times, you don't get a really exaggerated count. You're only counting that as 1. So we've talked a little bit about the envelope itself. So what actually is the envelope? So let's say I have a recorded time waveform from a step sine sweep stimulus. I'm going to remove the excitation frequency. And once I have all of my excitation frequency removed, I get my envelope. So what we're really trying to get here, again, is the number of times the threshold gets exceeded. I have an example here. I'm going to play the recorded time waveform, and then we'll play the loose particles waveform. So we can hear in context what was recorded, then we can hear what the recording sounds like with that stimulus stripped out of it. So that recorded time waveform output this loose particle envelope in green over here. Let's look at the analysis step to see what settings were enabled. We open this up, and I want to look at the loose particles tab. And I can see loose particle is enabled, loose particle waveform is enabled, which output that waveform that we listened to. My threshold is set to relative with the attack threshold of 8 dB. So to kind of visualize what that means, if we look at this envelope here, I have my envelope in green is normalized to 0, and then 8 dB above that is my threshold. If we zoom in, we can see all of these points here as times that the envelope crossed over. So once the threshold is exceeded and the minimum and maximum settings are met, then that counts as 1 loose particle. You can also see in some places the threshold will dip down minus 3 dB. And that is because we have our hysteresis set to minus 3. Every time we cross, we drop down minus 3 dB again until the signal goes below it. Once the threshold is recrossed after that, will count as another loose particle. If we scrolled along the top here, we would count out 12 loose particles have exceeded the threshold. That's really what we're looking at here. So this value of loose particle count of 12 is how many times this threshold was crossed. This was placed through a limit step. It was decided that we could have the threshold crossed twice before the device failed. So 12 greater than 2, I get a failure. We're also outputting the fundamental frequency response, the THD and the rub and buzz here. And for some of this data, this might be something that could be caught with harmonic analysis, but with this type of loose particles for this specific device, it was really only caught with the loose particle algorithm. There's nothing really wrong harmonically with the device. There's just something in there that sounds bad. Another example of this was when we used loose particles to catch air leaks. So this was going to be a transient type distortion. It's noise that's happening that might be harmonically related, but it might not be. So we'll run this again, play back a good waveform, and then a good loose particles waveform. Then we'll play back a bad waveform, then the bad leaking loose particle waveform. In the top left, we have the frequency response for both of those. The green was without the leak, and yellow was with the leak. We can see there's a little bit of a difference here in the high end, but where it becomes very apparent is loose particles, where green is no leak and yellow is with the leak. With no leak, we had a couple of times the threshold was crossed, but it was only 2. For the device with a leak, we had it cross the threshold 88 times. So that is obviously telling us we have an issue here. In this specific use case as well, we actually saw a large difference in the rub and buzz. With the device that leaked, there was a lot more harmonic distortion in the low end that was caught with the rub and buzz. So for this specific use case, a combination of the two, harmonic distortion and transient distortion, can both find and catch the same errors of the device, this air leaking. Again, some additional resources to look at here. We have a loose particle detection paper, as well as enhancements for loose particle detection. For more information just on how to set this device up in analysis, under our support portal, training, there's an analysis section, and part 5 will go over how to set up the loose particle tab. All right, so what we've been talking about so far has mostly been Harmonictrak testing, which uses a step sine sweep stimulus. So those are really good to set up. They're easy and they can be very quick. But the drawback there is sine waves aren't really what end users are going to be using the devices for. If somebody was purchasing headphones and listening to step sine sweeps, then testing with step sine sweeps are going to be all you need to do. But it's not going to be an accurate representation of what putting other types of signals through the device are. There's also some devices that just don't work with sine waves. If you have a smart device, one common thing it will do is try and filter out noise with DSP. There might be some signal processing on there, where if it hears a sine wave, it attenuates it, makes sure it doesn't come through to the end user. That's great when you're using the device for its intended purpose, but if you're trying to test it, you might not be able to get accurate information with the sine wave. Noise cancellation, compressors and hearing aids, different types of muting circuits, these all make it difficult to test finished devices and use sine waves to get really accurate results for how they're actually going to be used. Instead of sine waves, there's a couple stimulus options that we could pick instead. We could use noise, either pink noise or white noise. We could use speech, something like P50. We could use music, or we could use multitone. Noise and multitone are their own stimulus types. Speech and music most commonly would be used by using a wave file stimulus. Then in that wave file stimulus, pointing to the speech or music that you want to be playing back. But remember that Harmonictrak, for example, requires a step sine sweep, and TSR requires a log sweep. Some things are very specific. The analysis won't work with everything. So with these realistic types of test signals, the analysis that are most commonly used would be FFT, RTA, transfer function, and multitone. A lot of these are pretty similar. So FFT is fairly basic, and a lot of the other settings for RTA, transfer function, and multitone will share the same time and frequency configurations as FFT, but just build on them and give different options and different outputs available. So we'll start by looking at FFT. This will calculate an averaged FFT of the response waveform only. This is a little different from the basic electroacoustic test we were talking about with a stimulus and acquisition. We're not comparing the response waveform to anything. All we're doing is taking an FFT of the response waveform. You don't even need to have a stimulus. A very common application of an FFT spectrum analysis step would be a record-only step, getting background noise and running that background noise through an FFT. You're not outputting anything, you're just recording, and you're only feeding in one waveform to this step. If you are using a stimulus, then most commonly you could use noise. But no stimulus is required, or any stimulus could be used. We could look at an FFT of a log sweep, of multitone, of a step sine sweep, of a intermodulation sweep. It doesn't matter. It's just going to take your response waveform and run an FFT. The two tabs that are important to pay attention to, specifically for FFT, is the Frequency tab and the Time tab. The Frequency tab is going to be where we define our resolution. In the Time tab, we're going to define our weighting and windowing. So here is the Frequency tab for FFT. If you notice, we can't even click on distortion here. For this type of analysis, we're not going to get any distortion products out. Really all we're getting is an auto spectrum of the response. As we look at transfer function, we'll see how the initial setup is the same, but we can build on top of that. So the first thing we're going to do is define the resolution. Most commonly, we define it in hertz, so a 5 hertz FFT resolution. We could also select 1 over nth octave, though. Resolution is inversely proportional to the time required. So if I wanted a resolution of 1 hertz, then I would require a measurement length of 1 second. There's an option for spectral scaling. This should be set to RMS when using sine-based waveforms, and spectral density when using noise, speech, or music. This is going to affect all items with an asterisk. For FFT, the auto spectrum of the response is the only thing available, and that does have an asterisk. So everything on the Frequency tab is currently affected by selecting the spectral scaling. Here is what we can set up on the Time tab. At the bottom, we can output a time envelope of the response waveform, and we can specify Fmin and Fmax of that. But at the top, we can select a weighting. This is going to be the windowing that we use on the FFT. The default overlap will change depending on which weighting you select, or you could disable default overlap and specify your own overlap. The FFT length is a function of resolution. So on the previous tab, as we defined our hertz resolution, that FFT length is going to change. The number of FFTs is going to be a function of resolution plus whatever we select for the weighting. So why do we care about weighting? What are we doing when we pick these, and why does it really matter? So FFT analysis is done on signals that are finite, then limited to a specified window. We define the frequency resolution. That's going to affect, again, the length of the FFT. And if the data that gets acquired doesn't correspond exactly to one of the spectrum frequency lines, we can get spectral leakage. So this can cause amplitude errors and obscure adjacent frequencies. So if we don't window, we could get errors in two different domains, time and frequency. Windowing the waveform is going to help us with leakage, and it can give us more useful information. So how do we pick the right window and which weighting is appropriate for our use case? So here are a picture of the common windowing types that are available for us to select from the analysis editor. The first option is to select none, also known as rectangular. In red, we have Hanning. In green is Blackman-Harris, and blue is Flat Top. If we select none, there's no windowing done, and all parts of the signal are weighed equally. This would be appropriate if you were trying to take an FFT on just a transient if the entire transient was captured. The problem happens if what you're trying to capture and take an FFT of isn't exactly bundled up perfectly. Then we need to do some sort of windowing. Hanning is a pretty good compromise. It will smooth in both the time and the frequency domains. If you're just playing around with FFT, you're not sure exactly what the signal's going to be, you're still setting some things up, Hanning is a good default because it has the least assumptions on the amplitude, on the frequency of what you're inputting. Blackman-Harris works really well with harmonic and order analysis. It has excellent dynamic range and good frequency selectivity. Under Blackman-Harris, we have two different options, 4th order and 7th order. 7th order is steeper, so it has more side lobes, which can cause more ringing. 4th order is what we use by default in Harmonictrak because it's going to exclude the second harmonic from the fundamental. So if you're using Harmonictrak, anything with harmonic distortion, intermodulation, 4th order Blackman-Harris is a good weighting type to use. Flat top is pretty close to rectangular. It works well with sine waves when what you really care about is the amplitude and you care less about the frequency domain. So in our microphone calibration, for example, we use flat top. If I, instead of 1000 hertz, read 1000.6 hertz, I don't really care, but I very much care that the amplitude is exactly accurate. If instead we use Blackman-Harris and the frequency wasn't centered, then it might instead say 1000 instead of 1000.6, but it might sacrifice amplitude. So flat top is very, very good in the amplitude domain, but it might not be as accurate in the frequency domain. And again, these windowing types can be used in all of the different analysis algorithms that we're going to look at. So instead of an FFT, you could use RTA. RTA is a real-time analyzer, and it analyzes a signal using constant percentage bandwidth. So it has to be 1/n octave filters. Where we could define an FFT in 5 Hz resolution, I would need to define an RTA in 1/3 octave, 6th octave, etc. It's always constant percentage bandwidth. But similar to FFT, I can use it with any type of stimulus. Very commonly, it's used in telephony with speech. A lot of TIA standards will make references to RTA with 3rd octave with a specific wave file. Also commonly used with pink noise. Pink noise has equal energy per octave, and since the RTA uses constant percentage bandwidth, they work very well together. One major difference is that it also calculates the spectrum of the stimulus in addition to the response. RTA can compare the two and give us an overall frequency response calculated with the spectrum of the stimulus versus the spectrum of the response. If we look on the frequency tab, under curve resolution, I cannot choose anything besides 1 over n octave. So I will pick from this dropdown what octave band I'm going to be measuring. I can also specify the minimum and maximum frequencies I want output from this step. Under spectra, instead of just the auto spectrum of the response, I can now have a checkbox for the auto spectrum of the stimulus. Under functions, I could get a frequency response. It depends on the application. Sometimes you might only want to be taking the spectrum of the response waveform. If you're measuring noise or speech without a stimulus step, you could just uncheck stimulus, uncheck frequency response, and you would only be outputting the auto spectrum of the response waveform. And the stimulus and response spectra tie back to the waveform tab. These are just taking the spectrum of whatever's in your stimulus and whatever's in your response waveforms. We do have to be a little bit careful, though, with what we use for our delay. If an FFT or RTA spectrum is taken on just the response waveform and that's all we care about, our delay should be configured to set values and our offset time should be 0. What this means is it just takes the response waveform and does its calculations starting at the beginning. However, if we're using RTA to calculate a frequency response of a stimulus and response waveform, or even if we're using FFT with a stimulus step with an acquisition output, we'd want to change delay from set values to auto delay. This is so it's going to compare the start time of the stimulus with when that stimulus starts recording in the response waveform, time align them, and we can get a frequency response out. Again, just be careful of this. If you switch between using an RTA from frequency response to just measuring the response, check what your delay settings are. Transfer function, which is also known as dual channel analysis, is going to yield the true transfer function between the input and the output. So we have a stimulus, we have a response, and FFT is performed in parallel on both the stimulus and the response, which yields 2 series of spectrums. So transfer function is really meant to be used with 2 waveforms. It's trying to compare the input versus the output. It doesn't really do any filtering. It's just the input versus the output, all noise included. It can be used with any type of stimulus, but something that is broadband would be recommended. So you wouldn't often be putting a step sign 3 sweep or a 2-tone through here. Speech or music is recommended to be using with this type of analysis. When we have transfer function selected, we can get a lot of different things on the output. We can get the auto spectrum of both the stimulus and the response. So auto spectrum stimulus and auto spectrum response. the average cross spectrum between the stimulus and the response, the frequency response by comparing the two spectra, an autocorrelation of both the stimulus and the response, cross-correlation between the stimulus and the response, so that's taking the correlation of the stimulus and comparing with the correlation of the response, impulse response, and a signal-to-noise ratio. So there's a lot of things we can get out of transfer function. We talked about the auto spectrum. So the cross spectrum yields the average phase relation between the input and the output. This is calculated when complex averaging is enabled. This is calculated really only when we have something that has stable phase. We have the option in FFT-RTA, but we're forced to use power averaging because complex averaging is specific to only transfer function. But we can switch from complex to power if we don't have stable phase. If I was testing something with Bluetooth that had some sort of jitter, wasn't completely stable, using a smart device where I didn't have exactly stable phase, then I shouldn't use complex averaging. I should use power averaging. And this will give us an estimate of the frequency response based on the auto spectra only. Here on the left is my transfer function with averaging set to complex. Under spectra, in addition to the auto spectrum, I can get my cross spectrum, coherent and non-coherent power, as well as coherence, non-coherence, signal to noise, and non-coherent distortion. On the right side, when I have power selected, this looks a lot more like when I have the RTA analysis algorithm. It's using power, and I'm forced to only get an auto spectrum of the stimulus and response, but I can still compare the two and get a response. The spectral scaling here, you can see now there's a couple areas where the asterisk will come into play and some where it will not. And a reminder on this, spectral scaling should be set to RMS when using sine-based waveforms and spectral density set when you're using noise, speech, or music. It affects all items with an asterisk, and for transfer function, it would be recommended to use broadband type signals with spectral density. So one option we get with transfer function is coherence. Coherent power is the spectrum of the power present in the response waveform, which is coherent or proportional with the stimulus. So it's the linearity of those. Non-coherent power is the remainder. So if my environment was very noisy, if my program material, let's say I was playing music through a WAV file, didn't have signal above or below a certain range, or maybe there wasn't enough time to average that signal, my non-coherent power would increase. Coherence measures the degree of the linear relationship between the stimulus and response at each frequency. 0% is no relation, 100% is perfect. When coherence is the degree of linearity, non-coherence is the measure of non-linearity. It's a complement of coherence. If my coherence is 70%, my non-coherence would be 30%. We can also get non-coherent distortion. Here's a slide from an AES paper that Steve Temme wrote. that has to do with non-coherence distortion in headphones. If you're interested in reading non-coherent distortion, this has a really interesting setup, a good use case, and it's available on the website, and I'll link to it later in the presentation. A multitone stimulus is made of tones that are regularly spaced in frequency that will play back simultaneously. It's great for extremely fast frequency measurements. Because all of the tones play at the same time, we can quickly get a frequency response. We define the level, the resolution, the min and the max frequencies. But one thing I want to look at is this frequency rounding option. With this enabled, it's going to round all frequencies to whatever rounding value we have. So with this example, all frequencies are going to be rounded to the nearest 5 Hertz. Why would we want to do this? Because in the analysis step for multitone, I can configure my FFT resolution to be 5 Hertz. If I specify my stimulus to always play 5 Hertz and round to 5 Hertz, and my resolution in the analysis is set to 5 Hertz, this can really help avoid spectral leakage and make analysis very accurate. In the multitone, the amplitudes of frequencies are all equal, and the phase is optimized to lower the crest factor. And though it does use tones, the content occurs at the same time, and it's really much closer to real-world data. It can give us very realistic distortion components, especially when compared to step sine sweep or two-tone and even noise. It's also very easy to define in the stimulus editor. If I'm picking music, I need to make sure that the music has the spectral content. I can make those definitions in the multitone editor. Multitone analysis is the exact same configurations as transfer function. It has the same options. We can get coherence and non-coherence, non-coherent distortion, spectra on the input and the output. The big difference is frequency response in multitone is the amplitude and phase of only the tones that are present. Since multitone analysis requires a multitone stimulus, then RMS spectral scaling should be used instead of broadband that's often used with the transfer function. So thank you everybody for joining us today. Here is a list of a couple other resources available where we can get Steve Temmie's paper on distortion for multitone and non-coherence, the in-vehicle audio system distortion that talks about non-coherence distortion, and on the knowledge base, an article about how to use available weightings and which ones to use. If there's any other questions, feel free to shoot us an email at support@listeninc.com or give us a call. And thank you, appreciate your time. We'll again be sending out a survey and sending a recording of this video as well as the slides if you haven't received them. So thank you again. Have a good day.